So this is sentiment classification of movie reviews will be the next application that we're looking at. And we're actually going to look at this application both here in lesson 3 and then again in lesson 4. Only in lesson 4 we'll use neural networks. So we'll kind of get to see the same application but approaching it 2 very different ways. Is the font large enough on here, or do you guys want it larger? It's good? Okay. So I'm going to start using the FastAI library in this. And so I should note I have a bias. I'm co-founder of FastAI, but I do really like how this makes it easier to format our data sets. FastAI library is built on top of PyTorch. You can read some more about it in these articles. Let me know if you have trouble with installation. I highly recommend using Conda for this. And here we're not using the neural network piece, but really just being able to kind of load and format the data nicely. In lesson 4, though, we'll be using it for our neural nets. We'll be using the large movie review data set, which contains a collection of 50,000 reviews from IMDb. And this is part of FastAI Datasets, which was a partnership with AWS, hosting kind of a variety of data sets and making them easy to kind of download and format. Here's a collection of all the NLP ones. We'll use Wikitext later and the French-English documents later, but a lot of different data sets are listed here. I wanted to remind you, you can always, in a Jupyter notebook, use question mark to pull up documentation about whatever command you want to know more about. And so here I'm saying what is this URLs, and it's kind of giving me a list of data sets I can access via this. And I'll be using urls.imdb sample to start, and later we'll switch to the full data set. And this is kind of a good tip for any data analysis project. It's often nice to start working on a smaller sample to kind of make sure that everything is running, to be able to debug more quickly. And then once you have it working on a sample, then do it on your larger data set. So if you're doing anything has time-consuming steps, you don't want to be running those while you're still kind of just debugging and figuring out what you're doing. And here we just want to see kind of what does our data look like. So there's a label of whether a movie review is negative or positive, the text of the review. So here we can see unbleeping believable. Meg Ryan doesn't even, and even without reading, and we could see the rest of the review if we pull it up, but we could say, hey, that's reasonable that this is a negative review. The next one, this is an extremely well-made film, is positive. So that's the data we'll be using. I'm going to put this into an object called a text list. I can pull up documentation on that. But it has different items kind of containing the vocab, which is the correspondence between IDs and tokens. So what ID are you mapping to each vocab? How you're padding it. Oops. And then with any problem, it's good to see what our data looks like. So here, and the other nice thing about this text list is it's got a training set and a validation set and a test set, as well as it's got both the X's and the labels Y of what we'll be trying to predict with our classifier. So here I'm looking at, in the validation set, the first item. Here, this very funny British comedy show shows what might happen if a section of London, in this case, were to itself independent from the rest of the UK and its laws. This is a positive review. We can see category positive for the Y value. Does anyone know what these XX VOS, XX, UNK, what they are. Yes?
XX, UNK is probably just like a word that's unknown.
Yes, yeah, XX, UNK is a word that's unknown.
I'm actually not sure. What is that?
I think beginning of string for VOS, MAJ is a capital letter, and I've actually got a key a little bit further down. I was going to note something about UNK for unknown. Often, kind of FastAI, and I think many libraries let you set, if a word appears less than 3 times in the whole corpus, let's say it's unknown because you don't have enough information to learn about it. And so you'll have words that, are real words and may even appear once or twice in your corpus, but often you don't want to deal with them, so you just put them into this UNK. Although that can also include words that, are misspelled and only show up once ever. That's a kind of a bucket, and we'll look at what's in it in a moment. Yes?
So if you indicate, for example, that an entire word is all caps, the idea of like including tokens like these is you're trying to capture some additional meaning. So if you had like a review that was all caps, then that's probably going to be a very opinionated review.
Yes, that's a great point. Yeah, so having something in all caps, often that indicates that's telling you something about the language, that they're adding emphasis, they really feel something very strongly, and so we want to preserve that information, which is what having this kind of tokens that represent that do. At the same time, there's a similarity between that word and its lowercase version, and so this approach lets us get both of those of, okay, they're emphasizing something, and this word is the same as its lowercase version. Yeah, and let me actually now go to the meaning of the special tokens. Again, this is something that's going to vary from library to library, but what we've found very effective for FastAI. So UNK for unknown, PAD for padding. This will be more significant when we get to neural networks. The beginning of a string. Here, so actually MAJ is a word that begins with a capital, and up is, the whole word is all caps. Repeating a character is TK rep, that will have a number with it as well. So, I don't know, putting 10 exclamation points means something slightly different than putting just 1 or 2 exclamation points. That's another way of adding emphasis. And so here, this has all been handled. This data has been processed, and this is kind of how it's been tokenized. We can check the length. So we've got 800 reviews in our training set, 200 in our validation set. And remember, we're just doing a sample now. We're going to switch to a larger data set kind of once we have a better sense of what we're doing. So something to notice is that, so I2S stands for integer to string, and S2I stands for string to integer. And these are pretty different. So here, the vocab is 6010, looking at int to string, and it's 19,159 for string to int. Why would those have different lengths? Any ideas? Yes?
Explain again what int to string and string to int are.
Sure. That's a great question. Let me even. So here, this is nice. Movie Reviews has Actually, let me just make sure I've run all these. So movie reviews has a vocab. Actually, let me see what comes up. Yeah, so to get, oh, that's not. So into string, let's look at a little bit of that. So this is a list of tokens, and actually that might be more interesting. Let's look a little bit further down the list. That this new line was as, actually, 220 to 230. Bit, might, things, whore, us, almost, may, right. So this is a list of what tokens we'll be using, and it's also a way of mapping kind of, so each of these is represented as an integer. If you want to go from the integer to the string, this is how you do it. So you've got an integer and you wonder what token, what vocabulary word does this correspond with? You can look up the integer. So let me do. Let's see, what's the last one? Solette, which I don't know if that's a name, so if you, and we'll see this in a moment, we're going to end up representing our reviews as an array of numbers. But if you wanted to go from those numbers back to words, you would need to use this into string, is how you get back. And actually, from what I showed before, does anyone want to guess what order these seem to be in? Frequency. Yeah, so we saw, and actually let me put it up here so you can see again, that if I had the early ones, 20 to 30, these look like very common words that you would see, such as movie, that, this. So these are probably ordered by frequency, and so this is kind of our list, but it's, importantly, it's this mapping of, okay, when we have a number, how do we find the string it corresponds to, and then string to int is the opposite. So does anyone have a word they want to look up? How about language? For NLP, that's 917. And we could confirm that. So this is now if we are taking our words and we want to map them to integers, we're using string to int. And so what would we expect I to string of 917 to be? Language, exactly, because we're going back. And so we'll use these a lot of kind of going between the two. And typically it's whenever, if you want something human readable, you're often going to want strings to know what the actual words are. If you want something for your algorithm to process, you're typically going to want to turn them into numbers as your representation. And that's why we'll kind of have to be going back and forth as we inspect stuff and then as we're asking the algorithm or computer to do things. So going back to this question I had, so this is a mapping of going between two things. Why is there more in one direction than the other? Oh, like Maria?
Because when you look at string to integers, this is from one to many. So the same, several words can have the same frequency.
Yes. Well, it's not frequencies that we're mapping to. Although you're right about the one to many or many to one approach of string to integers.
Several words, they can have the same index. And, right?
Yeah, so several words can have the same index. And what are the cases where that happens?
So, for example, language is repeated multiple times. Then when we string to integer with multiple methods for word language, like when we do integer to string, then one same integer will
Yeah, although that's not what's happening here. So that would be the movies, the reviews themselves. When we convert the reviews into, we call this tokenization and numericalization, but we're going to, and I'll show this in a moment, we're going to transfer each review into this list of numbers. And there, yeah, a word can appear many times, such as language will appear many times. But what I to string and string to I are doing are kind of just our keys. And so language is actually only going to show up once because language is always going to be represented by 917. So here, and you might have a bunch of 917s if someone uses language a lot, but those will all be 917. But I'll show in a moment kind of what the reviews look like and how the same integer will show up a lot of times, or can. Other thoughts? Okay. And actually, are you guys open to using the catch box again, since these answers are getting longer and more involved? Yeah. Good catch.
So I guess like if you had capital L language, it might map to like two tokens, or you might have a lot of words that are unknown that all map to a single token, so that would make your like list of strings longer than your list of...
Exactly, yeah. So we can have a lot of words mapping to unknown. Many things will map to capital. Great. Yeah, so that's what's going on with these, is that many words are mapping to unknown. Let me see if I... Oh, and here, actually I'll come back to this. Here I'm just showing a bit of string to int, seeing how you can, from a string, look up an integer. This is a dictionary. What is, so string to int is a dictionary. What is int to string? A list, yes. Here I've made up a word, I misspelled my name badly, and showed that would get mapped to unknown. And then looking at the time, I guess this is a good time for our 5-minute break. So we will come back and create our term document matrix after the break, so 12:13. All right, I'm going to start back up because it's 12:15. And I would say a few questions I got asked during the break are good questions to ask in class. And so if you have a question about the content material, typically if you're wondering, other people may be wondering as well. So let me make a note. So I got one question about randomized SVD, which I think I'll come back to maybe at the end of class. Just so we can continue our train of thought on this, but on kind of where the randomized component was coming from. So maybe I'll say a little bit more at the end of class on that. And then another question I was asked was, let me come back up here. Why is this one a list into string, and why is string to int a dictionary? And does anyone in the class want to try taking a stab at answering that? Omer, and are you okay with using the microphone?
Sure. Because you might want to search by string.
You might want to search by string. Yeah, so a dictionary is good for that. So that's true. I'll take it back. Oh. So you could create a dictionary going from numbers to strings. Do you have an idea about why you might not want to?
It's just implied in the index? Or...
Yeah, it's implied by the index. And so it actually takes less space. Thank you. It takes less space to store a list. Oh. Let's see. Because note, with a dictionary, you're having to store the key and the value, but the integer is kind of implicit in a list.
So why aren't these just like functions? Why are these objects?
That's a good question. Why are these not functions? Why are they objects? So I would say you can kind of think of them as both, because, I mean, this is a function, it's giving you a mapping, but you have to, it's a way of taking inputs to outputs. And really that's what kind of what a function is, right? Often defined as a mapping to take you from an input to an output. And here that's something that cannot be generalized into a formula, but has to be stored as information. And so in that sense, you can think of really any list or dictionary in a way as a function that lets you give an input and come up with an output. Does that help, or?
I guess.
But yeah, there wouldn't be a way to, so typically when we think of a function, you know, in Python, that would be writing def, method name, etc. In this case, we would have to have some sort of object inside of there to store this information about how we get from the number to the string or the string to the number. Other questions about strings to integers or integers to strings? And I think it'll be nice as we go on, we'll kind of continue to use this, and so you'll get to see a little bit more, kind of get more comfortable with this. Oh, and here, actually, let me just make this clear. So if I was to run, I haven't run this line of code yet, what would you expect the output to be? Louder? Language, that's right. And that's because we're going to take that to an integer, which above we happen to see was 917, and then we'll take that back to a string, and we get language back. However, for this misspelled Rachel, that got mapped to unknown, so it came back to us as XX unknown. So this, basically, these mappings are almost inverses of each other, but because we have a one-to-many relationship and a many-to-one, it's not a true inverse. All right, so next up, let's talk about creating our term document matrix. In the previous lesson, we used scikit-learn's count vectorizer to do this for us. And today I want us to write our own, just to see kind of what goes into that, of how you take a collection of text and turn it into a matrix. But first, I want to introduce you to the ideas of counters and sparse matrices. Let me check, have you talked about counters in your other classes? Okay, some yeses and some sort ofs. But counters are super useful. So you can pass a list into a counter. They come from Python's collections, and it's going to create basically a dictionary with the frequencies. And so, and let me actually, yeah, so you can see this dictionary of frequencies. So here the values, the keys are 4, 2, and 8, because those are the numbers that show up in my list. And then we've got 2 4s in the list, 1 2, and 3 8s. And this is going to come in handy, I would say, repeatedly in NLP. So just keep this in mind as something we can use. Okay, sparse matrices. Oh, and I should also note, when you're coming up with the vocabulary, so you're doing the tokenization for a document or group of documents. So I mentioned earlier, you could set a parameter saying I want to have only words that show up at least 3 times in my corpus. You can also set a maximum number of words you want to have or maximum number of tokens. And that'll just take, so in this case, I think we've taken just the 6,000 most common words that we saw show up. But that's another way that you're kind of can cut down the size. Because we've gone from over 19,000 words to 6,000 words. But that's still a lot. And if we were going to represent this as a matrix, our matrix would have a ton of zeros. And thinking about space, that would be taking up a lot of memory space, even though a lot of it's zero. It's not that informative. And a matrix with lots of zeros is called sparse. The opposite of that, so matrices that don't have many zeros are dense. And for sparse matrices, you can save a lot of memory by only storing the non-zero values. Sparse matrices also, they often show up in a number of PDE type problems, and so you'll kind of get these representations sometimes, and this is a picture from Wikipedia, I believe, but here the white pixels all represent zeros and the black pixels are non-zero values. And you can have things that are, mostly zeros and also kind of have these interesting patterns about what's related. And I want to talk about sparse matrix storage formats. Both I think it's a useful topic to understand in programming and data science in general, as well as we're about to use it for our matrix, since we know most words don't show up in most reviews. And so I'm going to use some examples here. So let me find. Okay, so the first method we'll talk about is coordinate-wise storage. And a sparse matrix is stored using 3 arrays. And basically it's for each entry in the matrix, you want to store the row number it's at, the column number of where it is, and its value. So you have 3 pieces of information. And so I think this is kind of easiest to see with an example. So in the yellow section here, we have a 8x8 matrix, and we can see, so let's look at how 75 is stored. So this is in the row 6, column 4, the value is 75. And so we can store, you'll see down here, one of our entries is to say, okay, value 75 shows up at row 6, column 4. Another one in blue, 22 is at spot 1, 1, and we can store 22, 1, 1. There are questions about how this is being stored. And so just to kind of contrast how much space is used, here we have 21 entries in this matrix. For each one, we have to store 3 pieces of information, so you can think of that as 63 spots for storing things. In contrast, if you were going to store something for every spot in the matrix, that would give you 8 times 8, 64. So in this case, it's a little bit less. Although there are other considerations, that's kind of glossing over rows, and the row and column numbers are going to be smaller, so you might not need as much space. Like if you had decimals in your matrix, floats require more memory space than having like an integer or a short integer. So that was kind of glossing over some memory details, but just to give you kind of a general idea of, if you had a matrix that was 100 by 100, that would be a ton of spaces. And so it's really just the number of entries times 3 is what you're having to store in this coordinate-wise method. Any questions? Okay, and I'm also just going to point out how, the same value can show up multiple times. Actually, maybe it doesn't in this particular matrix, although it easily could. You would just be entering it in the value. And something nice about coordinate-wise storage is accessing matrix elements is pretty easy, because here you would look them up just by the row and column. So next, let me skip this. Talk about compressed sparse row data, compressed sparse row matrix storage. So here we'll store this using 3 arrays again. So we have one for value. We'll have column, which is the same idea of storing the column index. But now we'll have something called the row pointer that just contains basically it's going to tell us whenever the row index increments 1. And as a result, this row pointer array is able to be much shorter than the others. So in this case, this array is only of length 9. And it's a little bit confusing how they wrote it together with the volume and column ones, because it's shorter and it doesn't actually directly correspond to them. So I wish this was displayed in a different way. But here, let's look at a number. So let's consider 12. So here's the value 12. It shows up in column 1. And then to figure out the row is a little bit more subtle. What you have to do is consider that, so row pointer 0 means we have stuff that shows up in the, kind of starting with element 0. And then it is at index 3 that the values switch to the next row. So kind of coming over here, that 3 is corresponding to 0, 1, 2, 3. 22 is the first element in the first row, not in the 0th row. So we've kind of gone up to the next row. And so you can see that, yeah, so that's kind of telling, actually let me walk through these. So basically, so we have 3 elements in this 0th row. And so then the next one, we go to the first row. So you can think of this as element 3. I'm starting counting at 0 since this is a computer. So 0, let me count. 0, 1, 2, I go to a new row 3. Let me write down that 3. 4, 5, I'm going to a new row at 6. So let me write down a 6. 7, 8, I'm going to a new row at 9. Let me write down a 9. 10, 11, 12. Going to a new row at 12. Let me write down 12. There was only one item in this row, so now the 13th element is on yet another row. Let me write down 13. 13, 14, 15, 16 is on the next row. Let me write down 16. 17, 18, 19 is on a new row. Let me write down 19. And then here, I guess it's recorded 19, 20, and then if there was a 21th element, that would be me going to the next row. So basically, I was just having to write down whenever I went to a new row. Is that, and we'll walk through this again later, but this is, I mean, I think it's a little bit wacky to think about because it's a pretty different way of storing matrices. And so we have this nice relationship between the values and, oh, okay, we're storing the column number the same as before, and then this row pointer is pretty weird. It's just this list of me recording whenever I went on to the next row and started a new row. And we kind of had this default of, okay, I don't have to write anything down when I'm staying on the same row as before. How would you, suppose you are wondering which row item 8 is on. How would you figure that out? Let's start by looking at the matrix and just even finding item 8. Sorry, counting by 0 though. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So item 8 is 34. Yes?
You know,
oh, and actually, can I throw you the catch block? Oh, okay, okay. I was gonna walk part of the way. Okay, go ahead.
You know, item 8 is on column 3, and then it's between 6 and 9. So it's row 3, which starts with index 6.
Exactly. Yeah, and so kind of the key here is saying, okay, 8 is between 6 and 9, so it corresponds, in this case, it's going to be on the same row as the 6th element, which has index 2. So if you were counting at 0, it's 0, 1, 2, this row. Questions about this? So what do you think a benefit of this is? Louder?
Less storage.
Less storage, yeah. So if you got into a really big matrix, because notice this list of row pointers is going to typically be much shorter than however many elements you have. You're only having to store one number before, for each row. When else would this be good? Any ideas? All right, so there was a question, why does value 12 have row pointer 3? And so it does not. This is kind of a confusing way that this has been written. The row pointer, I wish that they had drawn this picture with values and columns next to each other and then like row pointer off to the side, because this does not correspond to the 12 or to the 1 here. Let me see. I have one other website I like to use. Let me see if they write it better.
I think the reason why they do it like that is because you can look at the row index.
Yeah, so one potential way they're storing it like that is because you can look up the row index easily. So yeah, let me show you this alternate way of representing it. So this is a different website that I linked to. Here we have different matrix, and here they've represented the row start index like this. So here they've got the column index and the data together. And it looks like they started counting at 1 instead of 0, just in keeping track of this. Let me briefly go through. Let me go through this example. This is a different way of visualizing it, and then I'll talk about the difference. But same concept of compressed sparse row storage. So 11 starts on row 1, so I wrote down a 1, and then I go 11, 12, 13, 1, 2, 3, 4. Item 5 is on a new row. So over here, I'm going to record a 5 because I've gone to a new row. 5, 6, 7, I go to a new row. Let me write down a 7 for my third row. 7, 8, 9, 10, 11. Let me write down an 11 for my fourth row. So this would be another way to represent this. Here, I think things are lined up a little bit better. You can see like, oh, okay, 14 is still part of the row that started at 1. What this doesn't capture is that this, what they called on the previous site, the row pointer, this is actually a very short array. Like they're have kind of added these spaces in so it'll line up nice. But in practice, you're not really storing spaces there. You're storing this just as 7 numbers in a shorter space. But this does show how, yeah, this 1 is corresponding to the first 4 elements. If you were to take these spaces out, things would no longer line up as well. But that is more accurate about how it's stored. Does that help, Maria? Okay, yeah, so definitely kind of sit with this. I'll put a question on next week's homework about this. This is a really kind of useful idea. I was going to say one of the times, let me go back to the, oops. Sorry, go forward to this one with the storage. So yeah, here, this 3 does not correspond to the 12 or 1 at all. It's kind of its own thing. So something that is nice about this is if you were going to be accessing your data by row a lot, this would be a really easy way to do it. It makes it easy to get a row of data since they're stored sequentially. You could pull these out. Here's a row, here's a row. So it's kind of a very easy, quick way to access rows of data. It will be much more of a pain if you needed to access a column of data in this format. So here, so 25, 45, 55, 65, 75 are all a column. That is not as easy to access because you're having to kind of do more calculation in between. Yes? Okay, so there was the question, can we convert the column to a pointer? So there is a compressed, I guess it's not in this one. There is a compressed sparse column method, which is basically the opposite of this. And actually, I think the other site shows that. Compressed sparse column storage, where here you are storing the row index for each element and then just storing when you go to a new column. So to count these, I would go 1, okay, I'm going to a new column for 2, 2, 3, going to a new column for 4, 4, 5, 6, going to a new column for 7, record the 7, 7, 8, 9, going to a new column for 10, record the 10. And so we've just kind of done the opposite thing. You want to do, I don't think you can do both simultaneously. So the question is, could you be just storing when you go to a new row and a new column? Because you need to have an order that you're traversing this matrix. And so, yeah, I don't know how you would do that. I don't think it's possible to say this one the row hasn't changed, but the column has, because you would have to be storing something that kind of makes this work is that we're choosing. And you'll hear this kind of talked about with algorithms sometimes if they traverse things by rows or by columns, but thinking about what order you're looking things up in. There are, however, a lot of different sparse matrix compression formats. So the only ones we're going to talk about in here are the coordinate format that I showed first, which I think is, I would say, the most intuitive. And then this compressed row storage and compressed column storage, which do show up a lot in practice. Then there are, though, a bunch of other formats for storing matrices, if that's something you're interested in exploring. And some of these are also taking advantage of knowing some underlying structure of what your data looks like. Let me go back. Forward to this one. So here they say some advantages of compressed row storage over coordinate-wise is the number of operations to perform matrix vector multiplication in both storage methods are the same. However, the number of memory accesses is reduced in the compressed sparse row storage. And something we're not getting into too much in this course, but I mentioned that moving things into and out of memory can be time consuming, and this is helping with that. All right, so let's go back to our notebook. So in SciPy, SciPy sparse matrices, the coordinate-wise format is typically how you're going to want to construct your matrix, since that's, I think, what makes sense to us intuitively to kind of know a value and its row and its column number. But then SciPy can handle that. Their conversions between CSR, CSC, and COO are efficient linear time operations. So that's something nice that SciPy can do, is switch between these relatively quickly if it is better to use a different format. So we're going to be constructing a CSR matrix, but we'll give it the information as COO, since that's what we know. So here I've written a method to get the the term document matrix, and we'll be sending it this list we have of all our movie review text. We'll want to keep track of so basically for each movie review, we're going to need to get the frequency counts of how many times each word shows up in that, and store values for those. So that's why we're using this counter on the data. And let me, I think even before I do this, so here we're iterating through our label list. Oh, did it run something up here? Oh, I see it. Sorry, guys. This is, we're just going to feed our movie reviews into here. So just to have an idea of what would each iteration of this loop would look like that we're going through. We would have our document as something like, sorry, train.x. So I'm not sure why this is showing up 3 times. Okay, I'll look into that in a moment. What we're doing here, though, is feeding a movie review in, taking the frequencies of the different words for it. Then we want using a counter, so to get this dictionary of frequencies, getting the keys and values for that, and adding them on to kind of the coordinates that we want to store. And then we'll pass these into the CSR matrix constructor. So we can call that on moviereviews.valid.x. Let me just check length of moviereviews.valid.x. Okay, yeah, so that's 200 movie reviews. Okay, here's the text of one. So this is what's being fed into one iteration of the loop. This would be the document. Then, and then we can look at data for that. Oh, and this is kind of getting back to a question that came up earlier. Is kind of how these correspond. So here, this is the text of the movie review. You can see this very funny British comedy. And then if we access that as .data, we're getting a list of, or an array of integers where these are representing the words in the text of the movie let me give a further example of that. So let's see what word 71 is. How could I look up word 71? Louder? I2S, yeah. So 71's an integer. We're curious. Oh, what was I calling it about? Oh, I was having it as the full kind of movie reviews.vocab. Later on, we'll store this into vary. And so this suggests, hey, it looks like 71 was the 4th token. 1, 2, 3, 4, this vary. And we could even actually, let me give like the first 10. So I bet, what is 189 probably going to turn out to be? What token? Louder? Funny, yeah. And so here, the way we're storing movie reviews in this text list is storing both the text version and the numbers version, but otherwise we could use these I to string and string to I to go between them. And so what we're doing is taking a counter on this. So let me call that now. So this gives us a counter, so we see, okay, vary only showed up once, funny only showed up once. And what showed up? Whatever item. 14 showed up 6 times. There are questions about that? Okay, let's see what 6 is. Oh, and that's uppercase. So there must have been 6 things uppercased in this review. And that's, I think, when something is in all uppercase letters. And so to get to our term document matrix, so again, we're kind of just trying to build the same thing that we had in our Excel spreadsheet of having, sorry, and I wish I hadn't done the normalized version, but having some count of, how many times did the word Emma show up in the book Emma, getting these counts. It's really useful to use this counter to get the frequency. Keep track of those and create our term document matrices. Now let me see, this is too big to display the whole thing, but let's show maybe, see if we can show the top corner. Oh, okay, and so since this is a sparse matrix, it's not displaying the whole thing, but it is giving us, I think this is neat information. It says, oh, there are 45 stored elements here. So even though I was showing a 10 by 10 section of the matrix, must be that 55 of those spots were 0, only 45 have values. And if we wanted to see it, you can, I don't remember if it's too dense or dense. I'll probably use this later on. Yes, too dense. Oh, that's what I do right here. Too dense converts this, and we can see how it looks. It's also kind of interesting to note, you would think the tokens at the beginning are the most common ones. So when we get down to the bottom corner, there's probably going to be way, or I should say anything along the far right of our matrix is going to have way fewer stuff stored. So let's try that. Oops. Oh, sorry, how do you go? Oh, I guess I want to go from -10 to the end. Oh, okay, in this case, there were 0 elements stored in this is just for the first 10 entries, but the last 10 vocabulary words don't show up often at all. So I'm curious how much, the last 10 only show up 10 times total. This is in all the documents. So this is kind of one of the benefits of the sparse storage. Are there questions about this? Yes?
For example, you're having, sometimes you might want to be because I was thinking about like SVD, and you can truncate.
So this is a question about SVD. Oh, can we truncate some of the things? Are you thinking about wanting to truncate kind of the least popular vocabulary words? And so in a way, we've already done this. Like this was just for the 6,000 most common vocabulary words out of, I can't remember, it was a total of over 30,000 words appeared in these. So you can think if vocab words 5,990 to 6,000 are kind of already this unpopular, how if we had tried to go out to 30,000 vocabulary words, most of those would have been showing up so few times. So yeah, in a sense, we've already truncated the least popular by not even adding them to our vocab. And we had to go through initially, to figure out, okay, what words are most popular and which are least popular. But that is something you could adjust if you said, oh, I want to do 5,000 vocabulary words instead of 6,000 to kind of get rid of these ones that so rarely show up. Are there questions about this? All right, so so I went to the next thing to kind of show how we can use toDense to convert this to a dense matrix to see what it looks like. And actually, let me remember, I always have to check what order the terms are in. So that would be int to string. So this first is for unknowns, and so you can see, okay, there are at least some unknowns, it seems like, in pretty much every review, or I would expect. We're only looking at 8 of them here, and some have quite a few unknowns. We're not really dealing with padding right now. Beginning of string appears once in each review because the way this is working, we've got one beginning of string. So that's not as useful here, but in a different application that might be useful. And then let me see what the last one is. Oops. I keep forgetting to split the order. It's from -1 to end. Let me think about, I don't know what these ones at the end are doing. Those don't seem to be, I'm sure those are not Solette, but what those values are, I'll update next time. Yeah, so here is just some more looking at the data. So I think we have time for one exercise. So here I decided to look at the review that was in spot 1 of the validation set. And it says, I saw this movie once as a kid on the Late Late Show and fell in love with it. And I said, since the word late shows up twice in this review, can you confirm that a value of 2 is stored in the term document matrix for the row corresponding to this review and the column corresponding to late? So let's just take a few minutes before the end of class to try this. But yeah, give this exercise, continue to try it at home. Shouldn't take too long, and then we can talk about it at the beginning of class next time.